Introduction. To satisfy energy demands sustainably, solar cells using quantum dots have emerged as low-cost, flexible options. While CD's quantum dots offer good performance, their cadmium content poses environmental risks. This study explores a green alternative by combining CDs with CIS, copper, indium, and sulfur quantum dots to reduce toxicity without compromising efficiency. Methodology. First, the FTO is washed with soap and water. Then it is placed in an ultrasonic bath with acetone ethanol for 15 minutes. Then the compact layer of titanium dioxide is deposited by spray pyrolysis technique with 0.5 milliliters of titanium disopropoxide is dissolved in 4.5 milliliters of absolute ethanol. The FTO is left on the hot plate until it reaches 500 degrees for 15 minutes. Then it is sprayed for 4 seconds with pauses of 30. The main function of this layer is to prevent leakage. Then the transparent and opaque layers that make up the mesoporous layer are deposited by screen printing technique. The transparent layer is deposited first, which provides the surface on which the CD's quantum dots generated by the Seiler method will grow. Then the opaque layer is deposited. This layer serves as a tool for the dispersion of the light passing through the transparent layer. This dispersion is beneficial because it will increase the possibility that the incident light is absorbed by the sensitizer. As a photogenerator are the CIS and CD's quantum dots, which are deposited by the Seiler method as follows. For the CIS quantum dots, the sample is first dipped in the indium acetate precursor, then allowed to drain out of solution, then dipped in an acetic acid-water solvent, which acts as a remover of excess ions, then dipped again in the copper acetate precursor, then dipped again in the copper acetate precursor. Then it is immersed again in a deionized water solvent. It is allowed to drain. Again, then it is immersed in the sodium sulfide precursor, it is drained again, and finally it is immersed in the methanol water solvent, and it is allowed to drain out of solution. This whole process is considered as a complete cycle for CIS quantum dots. For CD's quantum dots, the sample is immersed in the cadmium acetate precursor, then allowed to drain out of solution, then immersed again in an absolute ethanol solvent, drained again, then immersed in the sodium sulfide precursor, allowed to drain, and finally immersed in the methanol water solvent. For the whole selective electrode, there is a polysulfide-based electrolyte. What is achieved with this electrolyte is to obtain an appropriate redox couple. A copper sulfide counter-electrode was used as cathode in order to correctly catalyze the reduction reaction of the electrolyte. At the end, the cell is assembled as follows. A drop of electrolyte is added on the counter-electrode, then the sample is placed on top of it and characterized. Results. In this experiment, 2 factors were varied: the Seiler cycles of CIS 5, 8, and 10 cycles, and the cycles of CD's 3, 5, and 7 cycles. The experimental design was generated with the combinations of these variables, as shown in Table 1. For the photovoltaic characterization, monosensitized samples, pure CDs or pure CIS, were prepared optimizing the Seiler cycles number as shown in Table 2. It was concluded that the best performance for CD's quantum dot sensitized solar cells is obtained with 8 Seiler cycles, black curves in Figure 8a and b, reaching a short circuit current of 6.54, an open circuit voltage of 0.463, and a fill factor of 53.95%, resulting in a photoconversion efficiency of 1.63%, being in a good agreement with the reported performance for this kind of solar cells. On the other hand, best performance of pure CS samples was reached with 23 cycles, pink curves in Figure 8a and b, with short circuit current equals 2.34, open circuit voltage equals 0.402 V, and a fill factor equals 44.99%, corresponding to an efficiency equals 0.42%, a considerably lower performance than the 8 cycles CD's sample. The low fill factor and open circuit voltage suggest that although CIS samples have photogeneration properties, also have recombination issues. To solve those issues and use the photogeneration range of both sensitizers, several combinations of Seiler cycles of CIS and CDs were tested. Analyzing the effect of the CD's Seiler cycles with the CIS fixed to 5 cycles, it was observed that high amounts of CDs, 7 cycles, resulted in a very low performance, with short circuit current equals 2.73, open circuit voltage equals 0.336, fill factor equals 54.85%, and efficiency equals 0.5%. However, when the CD's cycles were reduced to 5, a considerable increase in the current was obtained to 5.23, resulting in a higher efficiency equals 1.04%. The improvement was even higher when the CD's cycles were reduced to 3, increasing both the short circuit current and open circuit voltage to 6.81 and 0.498 respectively, reaching an efficiency of 1.8% being a better performance than the best pure CD's sensitized sample. Similar trend was observed when the CD's cycles were fixed to 3, changing the CIS cycles, where the reduction of the CIS resulted in an increase of short circuit current and open circuit voltage see in Figure 8a. To better understand these trends, surface maps of the photovoltaic parameters as function of the CDs and Cis-Cds cycles were plotted in Figure 9a to d. Here it can be observed that the short circuit current increases with the reduction of any of the sensitizers, and that the increase becomes stronger when both sensitizers are reduced at the same time, reaching at maximum with 3 CDs and 5 Cis-Cds cycles. The open circuit voltage, Figure 9b, indicate when the CD's cycles are reduced to 3, shows a strong dependence on the CIS cycles, increasing as less CIS is deposited, reaching its maximum also with the 3 CDs and 5 CIS sample. On the other hand, the fill factor remains almost constant for all compositions with a small trend to increase when CIS is reduced and CDs is increased. As a result of the behavior of the 3 photovoltaic parameters, it has been obtained that the efficiency increases with the reduction of the CDs and the Cis-Cds cycles, having a stronger increase when both sensitizers are reduced at the same time, reaching a maximum of 1.8% with the 3 CDs and 5 CIS sample. Conclusion. As conclusion, multi-sensitized solar cells using CDs and CS quantum dots showed that CIS extends light absorption but increases recombination, which can be mitigated by using minimal CIS. Reducing CDs also improves charge transport. The optimal configuration 5 CS cycles and 3 CDs cycles increased efficiency from 1.63% to 1.80%, while reducing CDs more than half, making the cells more efficient and environmentally friendly.